All right, today we're going to step into the lab coat of a chemist. We're not just going to learn about salts, though. We're actually building a mental roadmap for how to create pretty much any salt you could need, right from scratch. So picture this. You're in the lab, and you're handed a task. Make a pure, dry sample of, let's say, copper sulfate, or maybe sulfur chloride. It's a fundamental challenge in chemistry, for sure. But it is not guesswork. There's a logical process, a decision map that pretty much every chemist follows. First things first, let's make sure we're all on the same page. When we say salt, we're not just talking about the stuff you put on your food. In chemistry, a salt is what you get when an acid reacts with a base or a metal. You see, the metal ion basically kicks out the hydrogen from the acid, and boom, you've got a salt. Okay, now we're getting to the heart of it. To figure out how to make any salt, you don't need to memorize dozens and dozens of reactions. You really just need to know how to answer one single, super important question. And this is it. This is the master key. Does the salt you're trying to make dissolve in water, or doesn't it? The answer to this one question determines your entire experimental path. It's the very first fork in our roadmap. So, how do you even answer that question? Well, with these, the solubility rules. This table here is your guide, and it shows how a few simple rules can be incredibly powerful. For example, just look at that top row. All nitrates are soluble. That one little fact is a fantastic trick that we're going to use in just a minute. Okay, let's take our first path. Let's say the salt you want to make is insoluble. It's not going to dissolve in water. This is actually the easier route, and it uses this really cool, simple technique called precipitation. The logic here is kind of magical. To create a solid that won't dissolve, you mix two liquids together that do dissolve. So how do you pick them? You use your solubility rules. Let's say you want to make insoluble silver chloride. Well, you know silver nitrate is soluble, and you know sodium chloride is soluble. You mix those two totally clear liquids together, and the insoluble silver chloride just appears instantly, like a solid out of nowhere. And the process itself? Super straightforward. You mix your two solutions, the solid salt forms, and because it's insoluble, you can just filter it out. Give it a quick wash with some distilled water to get rid of any junk, let it dry, and you're done. You have a pure, dry, insoluble salt. Okay, but what if your target salt is soluble? What if you need to make something like copper sulfate, which disappears completely in water? Well, this is where our journey gets a little more interesting and we come to another fork in the road. So the choice here all depends on your starting materials. Look at the left side. If one of your reactants is an insoluble solid, like copper oxide powder, life is easy. You can just add more than you need, add it in excess, and then filter out the leftovers. But look at the right. If both of your starting materials are soluble, you can't filter anything out later. You have to be incredibly precise. This is the whole key. Let's go down that first, easier path for soluble salts. We'll use the classic example of making those gorgeous, bright blue copper sulfate crystals. We'll do it by reacting sulfuric acid with insoluble copper oxide. So here's the method. You warm up some acid, and then you start adding the black copper oxide powder. Now the key is step 2. You keep adding it until some is just sitting at the bottom, unreacted. That's how you know for sure all the acid has been used up. Then you just filter out that leftover black powder, and you're left with a pure, beautiful blue solution of copper sulfate, all ready for crystallization. But hang on a second. Why bother warming the acid in the first place? It seems like an extra step, right? Is it just to make things harder? No, of course not. There's a really good chemical reason for it. Any thoughts? The answer is all about speed and efficiency. A warmer acid just reacts much, much faster. This makes sure that by the time you add that excess copper oxide, all the acid has definitely reacted. That way, you're left with a pure salt solution after you filter. It's a simple step that really guarantees a better result. And of course, anytime you're in the lab, safety is everything. I mean, even with dilute acid and gentle heating, you've got to be aware of the risks. The acid is corrosive, you have hot water, the solution could spit. This is exactly why stuff like eye protection is completely non-negotiable. All right, now for our final path. This is the one you have to take when you're making a soluble salt from two soluble reactants, like an acid and an alkali. You can't just add extra and filter it out. For this, you need the elegance and, well, the precision of titration. And this quote right here, it sums it up perfectly. The entire reason we have to do this more complex procedure is because filtration just isn't an option. You're mixing two clear liquids to get another clear liquid, so the only way to get a pure salt solution is to mix the exact right amounts, so absolutely nothing is left over. Now, this level of precision calls for some specialized tools. You'll use a pipette to measure out a super exact volume of one reactant. Then the burette, that's that long, marked-up glass tube, lets you add the other reactant literally drop by drop. It gives you total control. And finally, an indicator acts as your chemical traffic signal, changing color at the precise moment the reaction is done. The process itself is, well, it's meticulous. You measure your alkali with precision, add your indicator, and then slowly, carefully, add the acid from the burette until you see that permanent color change. You write down your volumes, and then, and this is so important, you do it again, and maybe again, until your results are totally consistent. And your results table might look something like this. You record your start and end volumes from the burette for each try. The titer is just the difference, the actual volume of acid you added. You can see here that runs 1 and 3 are really, really close to each other, so they get a check mark. Those results with the check marks, that's what we call concordant. They're the reliable measurements, the ones that agree with each other. You know, in science, you never just trust a single measurement. You're always looking for consistency. Concordant titers are your proof that you've done a precise and repeatable experiment. Once you have your concordant results, you just average them out. In this case, that's 24.65 cubic centimeters. That's it. That is the exact volume of acid you need to perfectly neutralize the alkali you started with. So now you can repeat the experiment one last time, but without the indicator, to get a perfectly pure solution of your salt. So, let's bring it all back home. We've got 3 different paths to making a pure salt, but it all starts with that one simple question: soluble or insoluble? That question, answered with the help of the solubility rules, is the key that unlocks the entire chemist's map. So now you have the decision-making framework, the map to tackle making pretty much any simple salt out there. You know the questions to ask, and you know the paths to follow. So I guess the only question left is, if you were in the lab right now, what salt would you make first?